Hey guys, welcome back to my YouTube channel. It's 2022. You want to hit that subscribe button and turn on your post notifications so you know every time I post. Hey guys, welcome back to my YouTube channel. So I need to stop that. So my name is Camille. If you don't know me, I'm the founder of Young Genius Tutoring Services. Yeah, so today I'm going to go through the 2021 question 1 of the CSEC physics paper. Of course, I'm doing this in parts because I'll be going through content as well. So I don't want to make the videos longer than they should be. So I don't want to make a 2-hour video. So, you know, I'll do you the courtesy of putting the other parts in the cards above. Just click the letter I at the top right, I believe, of the video. And as soon as they're up, they'll be there as well. And if you watch the video to the end, you'll see at the end card that the others will be there in a playlist as well, along with the next part or question 2 as another video link. So watch the video to the end and let's get into it. So the first question is 1A. It says state Hooke's law. So this is quite straightforward. So a little bit of advice: any laws, principles, anything you learn really in your physics journey, just commit that to memory. The laws, the principles, the theories or theorems, the postulates, especially the kinetic theory. Some postulates from the kinetic theory. Well, anyway, Hooke's law. So Hooke's law states, I'm sure that should say law, but bro, let's kind of delete that. Okay, that's nice. So Hooke's law. This I get trouble way too early now. So Hooke's law states that the extension, what is that though, of a spring is directly proportional to what? To the force, right? The force or load added or applied. Given that it's not done, this is the most important part of it. Given that the limit of proportionality is not exceeded, right? So once you have that, you have Hooke's law and you're done, right? So yeah, that is it. Hooke's law states that the extension of a spring is directly proportional to the force or load applied, given that the limit of proportionality is not extended. So basically, if you have a graph and you plot force against extension, you should get a straight line graph until you see that it starts to plateau. At the point at which it starts to plateau, about right here, that would be your limit of proportionality, right? And at that point, your graph will stop, or your spring will stop obeying Hooke's law. So it will no longer be proportional. The extension will no longer be proportional to the extension. And thus, a mathematical relationship that we can use to state this is F being directly proportional, that's a direct proportionality sign, to E. And if we want to convert this into an equation, we would replace the direct proportionality sign with an equal sign, and we'd insert what we call a constant of proportionality, will represent by K and E. So basically, this is the Hooke's law equation, right? And we'll find that if we want to solve for K, which is the spring constant, K would be equal to F over E, because basically you want to get rid of you want to get rid of the E on this side. So in order to get rid of it, seeing that we're multiplying K by E, will divide so that E cancels E. And whatever you do on one side, you have to do on the other side. So E cancels E right here. That's how we got K is equal to F over E. Now, if it were a case where we had plotted a graph of E against F, one thing, if we found the gradient of this original graph here, this gradient would have been rise over run, or the y-axis divided by the x-axis, and on the y-axis we have F plotted, and on the x we have E plotted, so F over E is equal to K by the equation. Now if we plotted E by F and found the gradient of this, we'll basically be doing E divided by F, which is basically the flipped version of F divided by E, or F over E. So that means that E over F would give us 1 over K, which is not the spring constant. So in order to find the spring constant K, we would have to find 1 over the gradient. Make sense? So, yeah. So the next part says to determine the spring constant or stiffness of a spring, a student placed different masses M on a hanger that was attached to a spring and recorded the length L of the spring. So table 1 shows the masses and the corresponding length values of length. So basically, I believe that the next question is going to ask you to complete the table. So once you've completed the table, you would have had enough, you would have enough data to plot your graph. So let's work with the table first. So let's work with force. So force by right is equal to mass times the gravitational field constant, and judging by the numbers here, the G value is 10. So basically you can just divide 1 into, or is it the other way around? So if it's a 10, we can divide 0.1 into 1 and you should get 10. So yeah, we're using the G value as 10. That's how you'd work it out if you couldn't just look at it and figure that out. But 0.2 multiplied by 10 is 2. And seeing that the answers before were written to 1 decimal place, continue with that trend to keep your table consistent. So 0.3 times 10 is 3.0. 0.42 multiplied by 10 is 4.2, and 0.50 multiplied by 10, so you put them in your calculator, 0.5 multiplied by 10 is equal to 5. Now this thing acting up, C5, so 5.0. Now for the extension, whenever the spring is not extended, then its length is 70.2. So this is the original length of the spring. So if you have a spring of length 70.2 and it extends 4.2 centimeters in length, that means the extension would be that 4.2. And the new length of the spring is 74.4 centimeters. So I hope you're getting the little difference between extension and length given, because this will be very, very much helpful in some questions, because sometimes you'll be asked to calculate the length, sometimes you'll be asked to calculate the extension. So keep that in mind. So basically, if we look here, we have 74.4 and an extension of 4.2. So we're basically coming from an original length of 70.2 and it was extended by 4.2 centimeters. That's how we got that new length at 74.4. Now, in a case where we don't have the extension, in order to find that, we'll subtract the old length from the new length. So basically, to get that 4.2, you would have subtracted 70.2 from 7.44. right? So we'll continue with that trend going down. So in order to find the new extension here, we'll subtract 74.44 from 79.2. So in your calculator, you want it to look something like this. So 79 point, right, the little dot, 2 minus 74.4. Hit your equal sign and we got 4.8. And you want to do the same thing. 83.9 minus 79.2. Are you good? 4.7. This 18.0 here is a huge mistake, and we're going to plot the point, but we aren't going to pull our line through it. So we'll see that later. So the real extension should have been, let's work it out, 88.2 minus 83.9, which is 4.3. So yeah, this should have been 4.3, but it's not, so we're going to leave it. And our next one would be 92.7 minus 88.2, which is 4.5. So now that we have our table completed, you get your 4 marks easy. CSEC nav nothing pan you, pop your color and let's move, right? So for the second part, they say using the grid provided in figure 1 on page 5, plot a graph of extension E versus F, force F. Now, I plotted it on Graphleaf because it was hell plotting it on the computer. So, a little bit of housewarming. Your graph should have a title. That's if they don't give you a title. And I believe this one already, this graph here, provided you with a title, so you don't have to write another title, right? It's right there. So the next part is to draw your axes. And once you draw your axes, you want to label them. So on the X, you should have a force here, force, comma, F, slash the unit, which is newtons. And you do the same thing on the Y, extension E in centimeters. Then you want to pick an appropriate scale. Most often you guys choose some odd scales, some of you. So don't go up by 7, don't go up by 25. Let me not say 25. I don't see you going up by that much anyway. But don't go up by 27, don't go up by these odd numbers that will be hard for you to find what the tinier lines, or thinner lines in between here, the value of those lines. Don't choose scales where you're not going to have a good time trying to figure that out, right? So what I usually do is count the squares, the larger squares that is. So I have about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I think it's 21. I usually divide by 21. 21, yeah, it's 21. So I usually divide the largest number on my table by 21 for the Y, and I think it's 10 on the X, but I'll count it. So depending on how many squares, just divide it by that and you'll find a scale quite easily. Anyway, let's look at the scale that I chose to this one. I chose a scale of 2 centimeters to 0.6 newtons on the x-axis and 2 centimeters to 2 centimeters on the y-axis, right? And that's because I had to plot that 18 centimeters. So if not, I would have chosen a much wider scale to get the graph covering more of the page per se. So here, if you look, the first points that we were supposed to plot is 0, 0, and I plotted it right here, right? Now, seeing that this is 0.6, that would mean that each line, meaning the thinner lines here would be 0.6 divided by 10, which is 0.06. So it values each of the tinier lines on the x-axis values 0.06 newtons, right? So that will help you out to find the other points. Now the second point that we're supposed to find is 1 to 4.2. So 1 would be around here. How do I know that? 0.6. So 1, 2, 3, 4, 5, 6, 7. 0.06 times 7. 0.06 times 7 is 0.042, and if I add 0.6 to that, I would get 0.02, which is the closest to 1. So I'll just plot it right there. Now the next one would be 2 to 4.8. So 2 is around right here, just as how I had found I had found that value for 1 right here. Did the same thing for this and brought it to 4.8. How I know that this is 4.8? Because each tinier line here represents 0.2 centimeters. So this would be 2.2, 0.4, 0.6, 0.8, and this would be 1. So 1.2, 1.4, 1.6, 1.8, 2.0. So here is our point at 4, and we need to find 4.8. This would be 4.2, 4.6, no, 4.4, 4.6, 4.8. So I'm correct. Then the other one would be 3, 4.7. So basically the space below 4.8 would be 4.7, because this would be 4.6, this would be 4.8, so in between here was definitely 4.7. Then our next point would be the one with the mistake, would be 4.2 to 18. So 4.2 is like right here. So if we bring that up, follow the line, our point at 18 would be right there. So right here. So we're on point so far. So this is how they check your points to see if they're correct, right? And based on the points plotted on your slope and thing, then we'll follow through from there on your graph to find out if your answer is correct. Because most of you, or yeah, for the most part, our values are going to differ depending on how you draw your graph. As long as it's drawn appropriate enough, you're good to go. So our next point is 5.0 to 4.5, and then we're done. So 5.0, somewhere before 5.4, I chose right here. Of course, I calculated it, of course. And yeah, I found the point to be right there. Then I drew a straight line from here to here to show Hooke's law. And then once it starts to bend at this point, this is the limit of proportionality that we're talking about, right? And or the elastic limit, and here is where we'll break at that point the spring will break. So spring breaks here where the graph stops. Nice. So once we've gotten that done, I guess we're ready to move on. So your graph should look something like that. As I said, for the line of best fit, it doesn't have to pass through all your points. It doesn't have to pass through any of your points actually. So yeah, this is not included in your line, so ignore it, right? So don't make the mistake of connecting your lines like this. This is a no-no. So some of you will actually connect from there to there, then from here to here, here to here. Then you're going to, let me zoom out a bit so that this is all clear, because this is a big no, 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 no. Don't do this. Shouldn't even be such a straight line either. So if your graph look like that, do it over. if your graph look anything like that, just do it over. Do it over. Alright? Don't submit your graph looking like that. You only conic points like that in bio. For chemistry and physics, you draw curves and lines of best fits. Alright? So all the best with your graph. Just don't do that. So I guess I can zoom back in, right? And we're good to go. So yeah. Let me try fixing this. No. I don't like this now, you know. So now this is giving me problems. Okay, I got it. Think I got it. Nice. So now that we talked about that graph a bit, you know, I made it easy to remember my scale. I put it there as a jotting. Of course, since I did this on Graphleaf, I still did myself the favor to name my graph so it'd be easier to find in the future, right? And yeah. So I actually gave this to the students in my class. So so use the grid provided, and we did that. So the next part of the question wants us to calculate the gradient S on the graph. So basically you're going to choose 2 points on the linear part of your graph, the straight line part of your graph, right? So I'm going to go with this point here because it's easiest, and 0, 0. So the points that I'm going to use are 0, 0, and I believe that's 4.2 to hold on. Oh no, sorry. So yeah, something wrong with my x value here. My x value. Yeah. So this x value is definitely not 2. It's less than 2. It should be, whoa, is it 0 point something? Yeah. So 0 point, let's work that out. So it is 1, 2, 3, 4, 5, 6, 7. Oh, I actually got this one. It's 1.02, I think, but let's work it out. 0.06 multiplied by 7 and add that to 0.6, and I would get 1.02. Yeah, so I'm correct. That's what I got originally. So it's 1.02. 1.02 for x and 4.2 for y. So those are the values that I'll be using. 0, 0. So 0, 0, and 1.02. I don't believe my mind's so shallow, you know. 1.02, 4.2. 1.02, 4.2. Now you want to find out what you're going to use for your x values, what you're going to use for your y's. So these are your x values for starters, and these would be your y's, right? So now you need to indicate what you're going to use for x1, what's going to be your y1, what's going to be your x2, what's going to be your y2. Now, if I chose this as x1, this has to be my y1. So this would make that my x2 and my y2, right? And the formula for calculating the gradient, in this case, they're marked it as S. You would subtract second y value from your first y value over your second x value from your x1 value. You could also do it like this. You could say y1 minus y2, but in this case, you're going to have to do x1 minus x2. So I hope you're seeing. So 1 stay under 1, 2 stay under 2 in all cases. But I'm going to use this first one. But however else you have learned to work out your gradient, do it like that, whichever way you're comfortable with, right? So my y2 value is 4.2 minus my y1 value, which is 0. This means that my x2 value would be 1.02 minus my x1 value, which is 0. So in this case, I can then put in my little, what these call now. Let me move this up a bit because it's kind of looking messy. Yeah. Okay, great. My units. So my y value would have been in centimeters and my x value in newtons, because I plotted extension against force. So basically I've gotten 4.2 centimeters divided by 1.02 newtons. Put that in your calculator. You're going to get 4.2 divided by 1.02, and that is 4.12. So seeing that you have the number after this second one here is greater than 5. So if 5 or greater, you're going to add 1 to the number at which you're going to stop at. And in this case, I'm stopping at 1. So I'm going to raise it by 1, which is going to make it 2. So 4.12 is what I'll write. So 4.12 centimeters per newton is my gradient S, right? Now that I've gotten that done, I can move on to part D. And it would be best if I brought this answer here with me. So duplicate and bring it. Great, so I have it with me. Make it smaller so it's not in my way, because these things have a way of being in my way. So now that I have this, it says given the gradient S is equal to 1 over K. As I said earlier, we know this. They even did you the little courtesy of just telling you, without instead of having you figure it out on your own. So S is equal to 1 over K, which is the gradient is equal to 1 over K. They want you to calculate the spring constant. So if you didn't know that you could just put 1 over S and find K, you can actually do a bit of transposition and make K the subject of the equation, and you'd be able to find the value of K. So S is equal to 1 over K. We want to get K by itself. So we can multiply by K on both sides. So if we multiply by K, whatever you do on one side, you have to do on the other side. So this K will cancel this K to make the overall thing 1. So we are now we're left with K multiplied by S being equal to 1. Now, seeing that we want K by itself, we have to get rid of that S. So we can divide by S, seeing that we're multiplying by S, right? So whatever you do, you do the opposite, and see we're multiplying by K. So we can now divide S by S to get rid of that S. So whatever you do on one side, you do on the other side. So this S cancels S to make it 1. So your K multiplied by 1 would just be K is equal to 1 over S. So now we can find K to be equal to 1 over 4.12 centimeters per newton. And basically these units will flip because it's the inverse. So 1 divided by 4.12 is equal to 0.24. So 0.24. Now seeing that the 2 that comes under it is below 5, we're not going to add 1 to the number that you're stopping at. So that's why we're going to leave this as 0.24. So K is equal to 0.24 newtons per centimeter instead of centimeters per newton. So I hope you got that. So the next thing that they want you to do is, given that F is equal to K times the extension, they want to calculate the length when a force of 8 newtons is applied, and assume that the spring obeys Hooke's law. Now, the force is in 8 newtons, and this is SI units, so it's basically 8 kilograms meters per second squared. So that would mean that that spring constant there that we have to change that centimeter to meter. So should have copied this with me because I'm going to need it. So duplicate, bring it with me. So nice. So we have K value in newtons per centimeter. So we're going to convert that. So 0.24 newtons divided by centimeter multiplied by 10 to the 2 centimeters, which is 100 centimeters over 1 meter. So centimeters cancel centimeters. And so we're left with 24, that's 24 newton per meter. So yeah, we have that done, and that's our value, the K value that we're going to use. So basically, if we have F is equal to KE and we're looking for E at this point, and remember we plotted extension, so then we're going to have E being equal to F over K, F over K. So now E would be equal to 8 newtons divided by 24 newton per meter, which this would cancel this. 8 divided by 24, you'd want to put in your calculator, so 8 divided by 24 is equal to 0.333 recurring, so 8 over 24 is at 1/3, which makes sense. So E is equal to 0.33 meters. So that's the extension. That's the extension in meters. So if we convert this back to centimeters, we're going to end up with a really small number, but hold on for a bit. Alright, so 0.33 meters is actually, let's convert that back to centimeters, is equal to 33 centimeters, because then we multiply by 100, right? Now, if we add that to the original length of, because this is telling us the extension, so it's telling you that it extended 33 centimeters if an 8 Newton force is applied. It seems quite ridiculous, honestly. Thing would snap by that point. So looking at this, the original length of this spring was 70.2 centimeters. So if we add 33 centimeters to that, we would get 33 plus 70. I don't even have to put this, isn't this 103.2? Let me check though. 70.2. Yeah, 103.2. 103.2 centimeters would be the length if it obeyed. Which number checks out. Very much so. So the number checks out. This would be 103.2 length would equal 103.2 centimeters, which would be the original length plus extension that we worked out a while ago, which is 70.2 plus 33, which would be equal to 103.2, and that would be the length of the spring when a force of 8 newtons is applied. And then it checks out if, assuming that Hooke's law is obeyed. So basically, if the limit of proportionality isn't passed, or the elastic limit. So the elastic limit is the point at which once it stretches the spring, it won't go back to its original length. And the limit of proportionality is the point on your graph where it stops obeying Hooke's law. So basically where you start to see a curve. And yeah, and the breaking point of the spring is where your graph actually stops. So I believe that was the last question, and just like that, you can get 25 marks, right? So yeah, remember, if you haven't yet, drop a like on this video, hit that subscribe button, and turn on your post notifications so you know every time I post. Share my content with a friend, help somebody out. Don't be selfish. Go follow me on Instagram. My socials are linked in the description down below, and if you watch my video, tag me on Instagram and me repost. All right, so again, thank you for watching, guys. Until next time, bye.